pleasure to have these three wonderful, distinguished blockchain experts to spend the next 2 hours with. And let me introduce them to you. So first, Qadeer, whose work on model checking and program analysis I've been following for many years when he was at MSR, at Microsoft Research. Then he moved to Facebook, and according to Google, he became the most cited researcher in Facebook who doesn't do machine learning or AI. True, I've checked. Then we have Andreas Rossberg, who used to be functional. And I do remember fondly his 2010 effing module paper, amongst others, of course. But there are titles that you just can't forget. We started interacting when he acquired State and was working at Google on JavaScript. We talked about benchmarking JavaScript programs. And now his State got corrupted by blockchain programming, and he's at Definity. Thanks, Andreas. And then Manuel Chakravarty, who also used to be quite functional some time back, and gave great and lively talk at Corion when I had invited him, and now he's on chain at IOHK.
Thank you, Jan. Thank you for that wonderful introduction. It's a pleasure to be here. So I'm here going to tell you about the work on the Move language that my colleagues and I have been doing at Facebook for the last 2.5 years. Let's start with some background about the project. So Facebook started the Libra blockchain project in 2018. And soon thereafter, we decided that it's going to be a programmable blockchain. So we needed a programming language. And after much deliberation, that language, started work on that language, and that language came to be known as Move. In the meantime, the Libra was renamed to Diem. So the current name of the blockchain project is Diem. All these technologies are all open source. You can find them on GitHub. So what is Diem? Diem is what is known now as a permission blockchain. Bitcoin is not a permission blockchain because it has participants who are trying to reach consensus on a log of transactions, and these participants are anonymous and they're not known to each other necessarily. But in a permission blockchain, all the participants are known at boot time. However, participants are allowed to change dynamically. So this is an interesting design point in the blockchain in the consensus space, because the network continues to exist, but its participants may change. So this is different from being a network that continues to exist despite participants being known at each time. Okay. So the reason this distinction is important is because known participants allow you to appeal to classic results on fault-tolerant consensus. In particular, we use Byzantine fault-tolerant consensus. We do a protocol whose roots go to the hot stuff protocol, but with many improvements. So consensus basically organizes. So there's a bunch of compute nodes, right? Any one of them can receive input commands. They pass commands to each other, and ultimately the idea is that all the commands have to be put together into an ordered log of commands. And then the implementation of each command is expressed in the Move programming language. To instantiate Diem, you need really just two things. You need some useful decentralized application whose computation is going to be replicated by the consensus network. In our case, it's an application that we call the Diem payment framework. I will say a few words about that. And then you need a group of participants who are willing to run nodes in the consensus network. So these are the participants that I was talking about earlier. The set of participants can change, but at every point in time, the set of participants is known. These participants are the Diem Association. So I'm making a distinction between Diem as a general concept, or permission blockchain as a general concept, and the particular instantiation, which is an application for us, an important application for us. So here are the Diem Association members. There are many organizations from many different kinds of businesses. So you'll see venture capital companies and recent Horowitz. You'll see Coinbase, which is a crypto wallet company. You also see things like Shopify, Uber. So, the main point that I'm saying here is that these different companies, they have kind of different incentives to join a particular network and agree to run a node. And this is, in fact, a very interesting social and technical aspect of the blockchain world. The incentive structure for participants to join a particular network. This is the bootstrapping problem, and it's an interesting problem in its own right. Now, let me say a few words about the Diem payment framework. So, there's state, right? And the state comprises a collection of accounts. And each account could contain one or more digital coins, more generally, digital representation of assets, permissions to do critical operations, and metadata about the membership of the network. Execution proceeds by transactions, and the state gets updated by these digitally signed commands that have been ordered into a log. So these commands include commands for minting, burning, and transferring digital coins, granting and revoking permissions, and changing network membership. I'll give you a summary of the results from the point of view of Move. So that was background. And then in the rest of the talk, I will tell you more about the Move language and the toolchain. So the Move toolchain comprises, there's a language, it has a compiler, it lowers source code to typed bytecode. So the bytecode is typed. It has its own independent bytecode verifier, type checker, that the bytecode is loaded by a virtual machine. It verifies the bytecode and executes it. And separately, there's a tool, a prover tool, which can do automated proofs of deep safety specifications. These proofs, importantly, are carried out on the bytecode semantics. One critical thing here in the architecture of the system is that we have taken many steps to keep the compiler out of the TCB, both in terms of what the virtual machine executes and what the prover verifies. Okay, so then the Diem payment framework itself is about 14,000 lines of code. The Move standard library is 1,000 lines of code. I just did a word count calculation on the source code, so I'm not trying to separate here specifications and comments from the actual code that gets converted into bytecode. This entire tool chain has been operational for more than a year in continuous integration, including the prover. And it has supported about a dozen contributors, but 4 main contributors primarily. For many months of that time of operation, the tool chain was being developed while the Diem payment framework was also being developed. And that was kind of an interesting, somewhat stressful state of affairs.
So there is a question in the chat. Artem asked, in what language are those 14 lines of code, 14,000 lines of code?
The Move language.
And how is it implemented? Maybe just out of curiosity, this is me asking.
Oh yeah, so I mean, it's implemented in Rust. Actually, in fact, the whole code base is implemented in Rust, and it has these tools that I was talking about. So there's a compiler, there's a virtual machine, and a prover. Prover uses the part that is closer to the front end, that's implemented in Rust. But we also use open source software components that make it easy to target automated solvers.
Somebody asked LLVM question mark, but I'm not entirely sure what's the rest of the question. So
I mean, so LLVM is clearly involved because Rust implementations, Rust targets LLVM. So it's kind of like buried deep there somewhere in our development stack, but we are, for the most part, not aware of it. All right, so Move is a language for secure transactional programming. First of all, execution proceeds as a sequence of transactions, all or nothing semantics for each transaction. So replication of that transactional execution is going on, but we can essentially ignore that replication aspect when we are thinking about Move semantics and the Move implementation. That's kind of like a lower layer concern, hidden, buried deep in the runtime. We don't have to think about that when we're talking about Move. The goal of a transaction is typically to update global state. The global state before the transaction results, it's examined during the transaction. The transaction is deterministic. That's an important point about Move. So the state at any point in time is a deterministic function of the transaction parameters and the global state at the beginning of the transaction. And the transaction finishes, it yields a set of side effects, and those side effects are applied to the global state. Okay. If the transaction has an exception in the middle, then the whole thing is reverted and the global state does not change. A lot of emphasis in the design of Move is to support local and automated reasoning. through a variety of techniques, including, simple type analyses, sophisticated type analyses, very sophisticated analyses based on automated constraint solvers, and so on. The key features of the language are modules. So, all of code is split into modules with clear interfaces and ownership of persistent global state. We have references. They add, ergonomics to the language. Sometimes it's very convenient to have references, especially for taking references to global state. We have linear typing. So, when we often worry about inadvertently losing critical resources, like a resource that represents an asset like money, or a critical resource that represents an asset like a permission to do a critical operation, having linear types in the system prevent inadvertent copying and dropping of these kinds of values. We also have generics. It's a parsimonious language, and it's deliberate because security is a high-level concern. Time was short, so we had to really prioritize heavily what we wanted, and we did not want to add any features that will allow expression of code that is hard to reason about. So, for example, we don't have dynamic dispatch, reentrancy, etc. And that. So here's a simple example. I wanted to show you some code. So here's a module bank. It has so a module is a repository for types and functions, right? So here you have one type. It's a coin type. It's a struct. It has one field inside it called val. And then you have operations here for creating, deleting, depositing, and withdraw. Let's take a look at one operation. So the create operation takes an address and a value, a U64 value. It creates a coin with that value in it, and it stores it in the global store. So this move to is putting something into the global store. All code and all global values, they are stored inside addresses. So after this move to coin succeeds, inside the address A, a coin value gets put, at most one value of a particular type. So you can put at most one coin in it. If you want more than one, then you have to have a container with some kind of a collection inside it. An important invariant that this module is trying to preserve is that all the coins that are published in global addresses, right, they have non-zero value. Okay, so this is an important aspect of module. So all the global state that is controlled by the module has ownership to it. So move to coin can only be done by functions that are inside, declared inside this module. Delete removes a coin. Clearly, it cannot violate the invariant. Deposit cannot violate the invariant. Deposit is interesting because it takes, it borrows a reference to the coin, to the instance of coin published at address A, and increments it by I. Okay, immutable. So it takes a mutable reference. Withdraw does the reverse. So it removes, it subtracts I from the coin that is published at address A. So again, there's a local check here, which makes to make sure that the value of inside the coin doesn't fall down to 0. And so we can reason locally here that the invariant is preserved by this module. Yep.
So what does abort do in this context?
What does borrow do?
Abort.
Yeah. Okay. So abort is evaluates that condition. If the condition evaluates to true, then it moves forward. Doesn't do. There's no side effect, right? Except that the program counter moves forward. If the condition evaluates to fall, then it's like a transaction abort. Then the whole transaction is dropped on the floor. Side effect without changing all the side effects. So in particular, if some global state was updated before the abort happened, then all those are dropped.
And what is the scope of this of the rollback? How far
it's the beginning of the transaction. Remember, I was telling you earlier that the whole execution proceeds in a sequence of steps. Each step is a transaction. So the scope of this abort is that transaction.
So there are two questions in the chat. Why can't coins have 0 values?
This is just an example. I just gave an example here. They can in general, but I was just trying to make a point here that should you want to have that invariant, you can have that invariant by using modules and by using the locality of modules. The fact that nobody else can change, can grab a reference to the coin type, no other module can do it. So that means, this is a way to reason locally.
And Dmitry was also asking, can you deposit a negative number?
So that is not possible because this value is a U64 value. It's unsigned.
Clarification, only one coin per address. That means values of others type can be at the same address?
Yes, that's right. So for example, if there was a coin 2 also declared inside bank, then you can publish inside an address, say 0xb, one instance of coin, one instance of coin 2.
I didn't catch that. You can have two things at the same address?
Yes. Yeah. Oh. So in an address, you can think of an address as a repository of a collection of objects. And each object is of a different type. To identify the object, you need to know what the type is. So you can't have more than one object of a particular type inside an address.
Okay.
Yeah. So in a way, this is different from memory addresses. These are think of them more like, like a wallet address. So where you have things of different types, different kind of pockets in that wallet.
Yeah. Okay. Aaron is asking, does that mean you don't allow U64 to wrap?
No, that's correct. U64 does not wrap. If, for example, let's take a look at this one here. This plus equals I, right? If this overflows, then that's also like an abort. It's an exception. And again, the transaction gets aborted. So here's the second important point about modules. So the modules can use other modules, right? Of course. So if a module M uses N, then there is a dependency graph of modules and there's an edge from M to N. So what we enforce in Move is that this dependency graph is acyclic. This enhances local reasoning about the global state controlled by M. Why is that? It's because you know that any outcalls done by M cannot change the state that is controlled by M because of this acyclicity. So this is again an enhancement of local reasoning. It also eliminates problem with reentrancy. You're able to reason about invariants locally. So for example, a lot of the attacks, reentrancy attacks in the context of Solidity and Ethereum, like the DAO attack, etc., they're just not possible by construction inside Move. Okay, now I want to show you some examples of linear typing. There is a struct permission inside this module access control. This is very abstract. I'm not going to tell you about what this permission is for, but just the idea is that if you put an instance of this permission in some address, that address gets some property, right? It gets some special privilege. You have an operation get to move the permission from address A and return it. So move from is the flip of move to. It removes something from global storage and puts it into a local variable. And in this case, that local value is then returned from the function. And this put is into an address. Let me show you a few pieces of code to illustrate what happens with linear typing. This piece of code here, it calls get, and then it just drops the return value on the floor, right? So this would be a bad piece of code. The type checker will flag this. This is another piece of code that grabs the permission from address A, copies it into Q, a different variable Q, and then puts it into a different address B. Okay. This code will also be flagged as an error. So dropping and copying are not permitted by default. This code bat2, you can make it work if you chose to use move rather than copy when you are moving the value from P to Q. And then this code would be okay. So by default, structs, they are not droppable and not copyable. Okay, and this is very helpful because you can put assets which should not be duplicable and which should not be lost. You can encode them as these structs and also permissions that represent critical access control. But oftentimes, you want to be able to use values as normal, so you should be able to copy them, drop them. In that case, you have these ability markers. They're similar to Rust rate markers, and you can put them on struct type definitions, and then you can do copy and dropping as you will.
What if B already contained a permission value?
Sure. So like I said, one address can contain only. If you try to put another one, again, it's an exception. So it's an abort. Or for example, if you try to do move from, or you try to borrow a type, a value from an address and it's not there, that's also an exception. So a few words about references. References in move are interesting because they have, borrow semantics. So in a way, they're inspired by the Rust language. Move, doesn't have a garbage collector. It has references, and yet it is statically safe. So the first example of an error is dangle after move. So imagine that you have a local variable C of some type coin, which has a field val in it. So if you take a reference R to the val field, and then you move C. So this move C is like, freeing that value C. Then you try to access R. This is a bug. So this will be caught statically. This is dangle after return. So if you have a coin and you return a reference to a field of it, this reference again becomes dangling after the function returns because its local state is torn down. This will also be caught. This one is a more interesting example. This is dangle after override. So suppose you take a mutable reference to C, right? And then you take a reference to a field of C. And then you overwrite Q. In a way, you are overwriting the value such that a reference to a sub-value of it exists. And this is also forbidden and prevented in move. So all this is done via a borrow checker style analysis. It's a sound modular analysis. So each function is checked separately. The core idea in the analysis is to model memory locations and references into these values stored in those memory locations as a directed acyclic graph, whose roots are reference. So the analysis is done modularly for each function. So for a particular function in the analysis, the roots would be all the local variables and the incoming references, and the non-roots would be local variables that contain references. Add an edge from, let's say here, from C to R after this operation in the borrow graph. Okay, and by maintaining this borrow graph at each control point and making sure that this gets updated based on an abstract operational semantics of each instruction, you can track the borrow relationships and you can forbid illegal operations. There's a formalization of it. There's a paper. There's a tech report. But this is all I'm going to say at this point.
Did you roll out your own borrow checker or use any of Rust's?
No, we rolled out our own borrow checker. So I think the Rust borrow checker, there are some descriptions of it, but because the move language is sufficiently restricted, we thought that we could do our own. So for example, Rust is more expressive because it allows references to be put inside structs. In move, references only occur at the top level inside stack variables. So this is one simplification that we could exploit to do something simpler. We don't have, for example, we don't have lifetimes. Another important thing is that we allow taking references into the global storage. So this is something that Rust does not really have. And we really wanted that feature. So we did a custom, we added something custom in our borrow checker for handling that safely.
Can you say what the soundness property is? Are there linearity check at runtimes?
For that, is Andreas's question about the borrow checker or the linearity checker?
No, I think it was more general about the type system, I guess.
So there is, I think that the type checker, you can think of the type checker has various pieces in it, So there is the part that is doing the type checking of the normal kind of type checking about values and generics and these linear types and so on. And then the borrow checker is off on the side. We have tried to prove separate theorems about each one of them, but we don't have a combined joint theorem for the entire language yet. But I think that theorem exists. By doing these, splitting out these theorems into two different parts and understanding each one of them, I think that we went a long way into getting enough confidence. I think it's still worthwhile to have a joint theorem, but we have not done that yet.
And do you have any runtime checks?
Yes, we do, like overflow, right? That's the kind of runtime check. But maybe you are not thinking about that. Think about the following thing. Let's say that you try to borrow a reference to a global in an address that does not exist. This will cause a runtime exception.
The question was specifically about linearity checks.
No, the linearity thing is completely handled by the static system. A few words about the move bytecode verifier. So as I mentioned earlier, our goal is to eliminate the compiler from the TCB. This is kind of important for a variety of reasons. So if you look at the compiler, it is more than 5 times, actually, I think it's probably 6 times larger, probably 6 times larger by now compared to the bytecode verifier. And it almost has to be this way because the compiler is providing a lot more functionality to the programmer. It's trying to provide nice error messages and many other things. The bytecode verifier is very parsimonious. All it wants to do is ensure safety of the loaded bytecode. So it doesn't try to be particularly helpful. And that's why we can make it small. It's much easier to make sure that there are no errors in a smaller code base. Other advantages of having a bytecode verifier is that loading code at runtime is faster. If we actually had a compiler in the runtime, a compile code, you'll have to run the compiler. It would be slower. And then finally, we can consume code from multiple programming languages. So these are the reasons why we chose to have these two separate representations of the program, source code and bytecode. So our bytecode is, by the way, typed. So all the type checking and references, etc., all the analyses that I was describing to you earlier, they happen both at the source language level and at the bytecode level. So in particular, the borrow checking is also happening at the bytecode level. The bytecode program looks like a collection of tables with the references into each other. And it is what you would expect. I want to say, I don't want to get into the details of this, but I will tell you a little bit about the things that is the most interesting, where the most heavy lifting in the bytecode verification happens. This is the bytecode instructions that comprise the definition of a function. The bytecode instructions, they define a stack machine that's operating on type values. So the idea is that the function gets a fixed set of registers they are roughly the input parameters and a few locals. And then for expression evaluation, you have to push the args on this stack, that is this implicit stack on the side, and then the results get consumed. The args get consumed, and the result gets pushed to the top of the stack, which you can then use for further operations. In addition to those kinds of compute operations, there are these global storage operations. So I showed some of those to you earlier, move from various versions of borrow and so on. The stack operations, the operations for computing on values, they are the typical general purpose operations that you would expect. So in the bytecode verifier, there are many kinds of checks that happen. So it's like a sequence of checks, starting from structural and going to heavier and deeper semantic checks. So you start with making sure that all the tables are well formed. Then you do some analysis of the instruction stream of a function. So we break up the instruction stream into a control flow graph over basic blocks. These basic blocks are for contiguous instructions. We have to make sure that each instruction only consumes what was something that was previously produced in the block with nothing left over at the end. We do type safety checking. So this is where all the fact, that values have appropriate types, and the values are used according to the type. The type checking with generics, the type checking with the ability markers, all this is done here. And then we have a separate pass on the borrow checker, which guarantees reference.
There was a question about whether the language is higher order.
No, it's not. We don't have functions as first class values.
And then somebody asked, is there recursion? Do you prevent infant loops?
Recursion is allowed. We do not currently prevent infinite loops. In other words, we currently do not have a way of proving termination or proving any kind of complexity bounds on the execution of the program. What we instead have is gas metering. So dynamically, we make sure that a transaction does not take more runtime than what it claimed it would when the transaction was submitted. So this is a concept that is popularized by the Ethereum VM, where when a transaction is submitted, it comes with it some gas, and then it should not take more than that amount of gas. And that's enforced by runtime verification. I have done some work on static gas estimation with Ankush Das. That is interesting, but it was inspired. The language that we used in that analysis was inspired by Move, but that's kind of a separate work. There is no implementation of that in the Move system right now. Now I want to move to the part of the Move toolchain that is the deepest in terms of semantic analysis. So this is the Move prover. So here the goal is to prove deep safety specifications about things such as access control and invariants preserved by modules using automated reasoning. We have a pipeline, in our tool chain. We have the front end, which takes Move code annotated with the specifications. The code is compiled into the bytecode and the specifications. Then a formal execution model of the bytecode is constructed in a modeling language called Boogie. the specifications are also compiled into Boogie. And then using the Boogie analyzer, we check that the specifications are met by the bytecode semantics. Boogie internally uses a collection of techniques based on verification conditions. So the analysis is modular. Each function's code and specifications, it gets converted into a logical formula and it's verified automatically by an SMT solver. If the SMT solver says yes, then that function is verified. If it says no, then it generates a model, and that model can be mined to yield an execution trace that can be then displayed at the source level. This gives you a rough sketch of what specifications look like. So specifications are also laid out inside modules in various places. You have specifications attached to functions. These are the classical specifications based on Floyd-Hoare logic, preconditions, postconditions, modifies. We have a new kind of specification called abortsive. This describes precisely the conditions under which the function aborts. Then we have invariants. So remember that I was earlier showing you a module bank which had an invariant about the set of all published coins in that bank, right? So those are the kinds of, and we said, all the coins that are published in that bank, they are non-zero. So that kind of invariant you can state at the module level over here. We also support invariants on structs. The scope of these invariants is different. So these invariants that are defined in the scope of a struct X, they are talking about all values of that struct X, all stable values. So meaning that all values that are currently not being, that currently don't have a mutable reference on them or somewhere inside them. Whereas the invariants at the module level, they're about invariants about all values that are published of the types that are declared inside the module. You can, what is the expressiveness of these specifications? Well, I mean, they can refer to variables, local variables, as well as global variables. And they have all the logical operators, Boolean, arithmetic. We have vector types, so there are useful operations on vectors. And then finally, we have quantifiers. So an important aspect of building a prover, like the move prover, is to model the operational semantics. So here you have to, a big challenge is to model the memory. So in move, as I was indicating, the memory is tree structured. So its values are records of records of records. So you can think of the entire memory as a forest, a collection of trees. So we have to somehow model that in logic. One thing that causes complications, as always, is references into memory. These are essentially pointers to subtrees in that forest of trees. They can be stored on the stack. They're stored on the stack, either in local variables or in parameters. We have this restriction in move that references cannot be stored inside the forest itself, and that helps us. We exploit the borrow checker. The borrow checker computes information that allows memory updates to be modeled using copy semantics. So what do I mean by that? Big problem with the references is that when you have mutable references, you have to model indirect updates. So this is difficult because, imagine you have a problem like this where you have a tree T1 and it has a subtree T2. You have a mutable reference pointing to T2 and then you modify something inside T2. In fact, by doing that, you have actually modified the value T1. So if there's a variable which contains T1 inside it, you have in fact modified the value of that variable. This is difficult to model, but the borrow semantics and the borrow checker aids us a lot because we have an ownership model that is enforced by the borrow checker. We model this kind of mutation using copy in, copy out semantics. So it's as if this T2 is stored, it is a separate entity T2, and then we modify it. And when this reference dies, we copy this back into this value. So that way we know we have this idea of a delayed write into the variable that has T1 in it, and it becomes more functional. So we model immutable references as they become values, right? We are able to transform the program completely. So we model immutable references as values, and mutable references are handled via copy in and copy out memory model. So essentially, by the time we get to Boogie, references have been compiled away. And this is very important because for scalable reasoning, because it greatly simplifies framing. It avoids need to specify memory that functions do not change. And so we are able to marry the convenience of imperative programming with references with the reasoning advantages of functional programming. I'll just move to the results. So I just wanted to remind you about a point that I made earlier, that this entire tool chain, including the move prover and all the specifications that were written on move, they are in CI and have been in CI for a year at least. This is, I think, in my mind at least, a big step towards making advanced tooling. And move prover is an example of advanced tooling accessible to developers. just making it routine to be used in normal code development practices. So we have about 14,000 lines of code plus specs plus comments, and there are many specifications. So we focused on access control because they're a really important part of our security specification. Driven by access control, we wrote invariants about global state that allow us to reason about those specifications modularly. And then we added preconditions, postconditions, modifiers on function boundaries as necessary to scale reasoning. A big problem with using things such as automated constraint solvers is that they have worst case high complexity. So you can't push large volumes of code on which rich specifications are being checked. So if you're trying to check rich specifications, which we are, then you have to kind of like decompose the problem into pieces. And we try to do that using function boundaries. Performance is good of the tooling. So the move prover takes about 30 seconds on my laptop for this entire code base, that 14,000 lines of code. So this is just to say that the tool chain is fast enough for interactive development when it works. I mean, we all know that the bulk of the time comes in actually writing the code and the specifications, but you still need the tooling to be fast so that we can provide quick feedback. But there are challenges. The tooling is fragile because of the dependence on decision procedures that have heuristics in them. They have high worst case complexity. So we often find that small changes in programmer specifications lead to timeout, or for example, small changes in environmental conditions. So things might be working fine on my laptop, but in CI, there might be a problem because that's a different computer running in the cloud somewhere. Specifications summarizing procedures often become verbose, and we would like to get around that problem. So, the ideal would be where developers write the specification that is the most meaningful, and all the supporting specifications that are added just for making reasoning scale, they are somehow automated, but we're not there yet. Finally, modular reasoning about invariants remains difficult because purely local reasoning about state somehow seems to be difficult. We often need to write invariants that connect state published in different modules. So now you have to worry about when you have a network of modules, if you are entering a module from two different paths, let's say, have a module C and A and B are two of its clients, then could it be that when you enter C from B, it could create some problems for the invariant in A that is referring to the state of A and C. So there are challenges like that also. Okay, so at this point, I'll stop and I'll take questions.
So what I'll do is before we go to the question, I'll let Andreas and Manuel speak, and then we'll take questions and sort of feed them to everybody. Manuel, do you want to start?
Yes, thank you. Thanks very much for the talk. It's very interesting. Yeah, so I think looking at the bigger picture, generally of languages for smart contracts, or whatever you want to call it, on blockchains, to my mind, the most interesting contribution of Move is the use of linear types. And maybe for other reasons than a programming language audience might expect, because, well, we have Rust and there's some other language codegent and so on who've used linear types for comparable reasons. But in blockchains, what we've blockchains are kind of a layered setup, right? We've got a consensus protocol, which ensures that all the different block producers or transaction processors, this is just called them, agree on the ordering of transactions. And then on top of this consensus protocol, we have what we call the ledger rules. They talk about the movement of coins and things like that. And then we have contracts, which are used to create what some people call programmable money, or kind of applications on top of a blockchain. And classically, one important, crucial point that is confined to the ledger is what blockchain people call the double spend rule. So if I've got one Bitcoin, then I can only use that once. And this is actually encoded in the ledger rules of Bitcoin, and Ethereum has something similar. Cardano has the same setup, where, yeah, these what's just called resources, which can only be spent once. The tracking of that constraint is usually encoded in ledger rules. So now the choice here is to take this, what's usually in the ledger, and kind of lower the responsibilities of the language down into what other chains use the letter rules for. At least part of it, this double spend or linearity, single use type of restriction. And I think this is really the conceptually most significant distinction of this work, as I understand it, which is very interesting, and I'm curious to see how that pans out. I mean, one advantage, for example, as just said, is that you can have many of these resources, so having multiple different types of coins is very easy, whereas other chains, like, for example, Bitcoin doesn't have this ability, Ethereum doesn't have this ability, and Ethereum, you do a whole big dance to achieve similar things. Then other chains like the Cardano blockchain, they have an increased set of letter rules, a more powerful set of letter rules, where the letter rules allow you to have an unbound number of these linear tracked resources. And yeah, so I would be curious just what your thought is on this kind of like shuffling of responsibilities between letter rules and the programming language.
So maybe before replying, let's also get Andreas, and then we will launch the discussion off. So hold those thoughts. Andreas.
Yeah, okay. I'm not sure how to exactly follow up on this. But so, well, first, maybe a confession that I don't really know much about blockchain at all. I'm more like a language person. So, but one of the things that interests me is like how these things are actually related. So we're talking about blockchains, we're talking about smart contracts, and in most of the blockchains right now, these two notions are very closely related, right? So you have a smart contract language that maps in a very specific way to a specific blockchain, and you have usually a specific language for a specific blockchain, or maybe you have a number of them, but they are not like portable or general purpose like we are used to from other domains. And that is despite thinking, or you should think, that smart contract languages are really just a form of DSL, right? So why are they so closely tied to a specific blockchain is one problem that interests me, and whether these things can be decoupled. So one thing we do at Dfinity is we try to decouple these, right? So, and there were some interesting things actually with the Dfinity blockchain. We initially also thought that we built in like the ability to transfer funds something, and we wanted to have the ability to define as many funds as you want, right? So there's not just one magic fund on the blockchain, like Manuel just said. That is the case in most of these, but there could be n, and they could be user definable in some way. And we had a whole design for that, and turned out we had to scrap it all because there was no way to make this like compatible with some of the APIs we had to talk to. Like I think once the Rosetta is what one of them is called. So ultimately, we ended up just implementing the ledger that represents the funds, the ICP token in user space on top of our blockchain, right? So it's actually a layer up. And that was more for practical reasons than that was initially even intended. But yeah, so this is kind of like my angle. Maybe are we missing some abstractions here? Are we still like thinking too low level about these things? And where could we go from here? Mm-hmm. Or is that even a good idea to think more high level about these things?
Right. So Shaz, do you have any sort of quick comments before we go to the question to these points?
You know, I mean, I just want to say that I've struggled with exactly the same issue, and everything that Manuel and Andreas said, it's kind of like exemplifies my journey through this space. I've been very puzzled, you know, first of all, why do we need so many blockchains? And then second, why should each blockchain have its own language? And I think that to me, it is an indication of the relative immaturity of the field. Even though Bitcoin has been around and functional for a while, I think that we are still struggling to come to terms with what the compelling applications are and how do we architect an infrastructure, language and system infrastructure to solve those applications. going back to the specific question that was raised about the use of linearity, I mean, I think that the idea that you, one thing that we take for granted now in Move is that the fact that something is money or an asset is really in your head. At the language level, it is just some type annotations. This seems so trivial to people with a PL bent, right? But it may have been a breakthrough at that time. And I'm really glad that we are going in that direction and not trying to build custom one-off solutions for this, that, or the other, and having some generality. So for example, in our case, we discovered that once you have these general language mechanisms in place, you start to build scaffolding, not just for reasoning about assets, like relatively minor things that assets are not getting duplicated and so on, but even things such as access control. So I didn't give you like detailed examples of it, but you can encode access control patterns in a fairly compact way using linear types also. I think that's something that still we're trying to wrap our heads around and trying to explore it. Okay, so that's just what I wanted to say in response to the comments by Manuel and Andreas.
Can I respond to that? Yes, I'm kind of glad you're saying that you can implement access control going this way, because I think it shows really we have some sort of duality here, and usually maybe one way to think about it is in a language we always have a runtime system, right? And in a language implementation, and sometimes you have a trade-off. Some capabilities you can put into the runtime, or you can put it into the language proper. And very often it's also not clear-cut. It really depends a little bit. Sometimes this is better, sometimes that is better. And so what we found, so in Cardano, where the ledger is really very much following the Bitcoin approach, using UTXO model, not an account model, and where Bitcoin only has one coin, we introduced what we call the multi-asset extension of those ledger rules. And we call it multi-asset, but basically what the ledger rules enforce is a sort of a linearly threaded, programmable and creatable resource, which we call an asset for historical reasons. But we found the exact same thing. So we started to encode basically permissions in a style-like capabilities, like in a capability-based operating system, by defining assets which convey a particular capability or role inside the contract. So even if we have this functionality, once we generalize it to be programmable and not like one-off like Bitcoin or Ethereum, then we get this ability to talk about permission capabilities, regardless of whether that's in the language level or on the ledger level. And I'm not saying at all one is better than the other. I just find it super interesting, just from a the researcher in me point of view, that you're doing this experiment of making the other choice, right? Saying, okay, we want this not in the runtime system, we want this on the language level, and then we'll see. Like now, we actually can have this experiment of a system where you have this other choice, and we'll see how that pans out in practice in comparison to, let's say, the historical classical choice. So that was for me always, the most interesting thing when I read about Move. Yeah,
the funny thing is that I always took it for granted. I think it's because I was just not, when I came into the community to work on this, I had not, drunk the blockchain Kool-Aid or the Bitcoin. So it's not like I was taking all those things for granted. I was just doing the thing that seemed the obvious, natural thing based on my training.
Yeah. That's interesting. And to Andreas' point, I think one reason why there is a language for blockchain is just historical. People set up a blockchain project, and then it's somewhat different than previous ones. So, for example, Solidity, and for especially the EVM, the virtual machine, for coupled to the setting which will have implications for the language. So they are just super tightly coupled, and maybe that's a sign of immaturity. That maybe now, for example, in the case of Cardano, our intermediate language, we wanted to be as little custom as possible. So we picked the lambda calculus, which at least is maybe not a standard intermediate language, but at least something well known, broadly shared. And as a result, I mean, we use Haskell to write contracts, but you could use other functional programming languages as well. It's just that somebody has to implement the toolchain. So I think the coupling is really more between the virtual machines and the blockchain. And then it depends on how flexible is your virtual machine in supporting different sorts of languages, at least current state of the art.
It seems that there are still like various abstractions that leak through, right? Like it's like payment is one thing, but also the whole notion of a block and that of gas and all these things, which are also specific to you or different across blockchains, it seems. And you have to cope with them somehow on the language level. And there's like no established generic way, as far as I can tell, how to model that really. It's usually very ad hoc and very coupled with a specific chain. At least that was my impression of this.
Absolutely. And I mean, in the case of Cardano, we make an effort to get away from that. There's no notion of blocks. There's a notion, abstract notion of ticks of time. That's all. There's no gas. That doesn't leak through. It's fully deterministic. You know exactly what the execution time of a piece of code is. So I think you're right. It's a maturity thing. It's something where we try to learn how to get more abstract environments to write these programs in. But it takes time, of course, because each of these is hard to get rid of, each of these dependencies.
I want to raise another point to get the panelists' opinion, which is transactions. Would you say that the transactional model that is used in Move is there a common there's consensus that that's a good thing to have, or is there some dispute about using transactions also?
I think transactions is totally fine. I mean, that's I mean, there is this, I believe in Diem, you don't chop the transactions up in blocks. There are some other chains which also do that. And then there's this traditional kind of chopping them up in blocks for mostly kind of networking reasons. But at the end of the day, it's always transactions. I think the big divider here is whether you insist on making the transactions into one linear sequence, logically, also semantically, like Ethereum does, like I assume Diem does, because it uses an account model, or whether you follow Bitcoin's model where the transactions are in a DAG, in a directed acyclic graph. And Cardano, for example, follows this model, but there are some other modern chains, Nervos, for example, Ergo, but because Ethereum did this step moving away from UTXO to account-based model and this totally linearized chain, people have come to associate UTXO means you don't have a lot of programmability. Account means Ethereum style, you can do everything. But in reality, this is actually just a historical connection. It's not essential to that if you want programmability, you need accounts. That's actually not the case. So maybe this is still the only. So why would you go to this graph structure? Well, it has more parallelism, and that's good in a distributed system. That I see as the main distinguishing factor where you can basically all projects I know about, at least you can put into one of the two buckets, account-based, fully linearized, UTXO-based, directed acyclic graph.
Yeah, I mean, more generally, I think this is a question. I mean, transactions, I think from the user perspective or application perspective, of course, are highly desirable. The question is how scalable they are, right? So if you really, I mean, so right now, like the first generation blockchains, they have scalability problems, and they are related, I think, to some significant degree to their use of transactions throughout, or very, very rigid use of transactions. And the question is how you want to scale that. So one thing that everybody has been working on for the past couple of years is to introduce what some people call sharding, right? So that you actually don't just have one chain, but can have multiple chains that can interact with each other just as a way of scaling out. And then you have all the properties of a distributed system, essentially, because these chains are no longer like there's no single centralized entity anymore that runs. And then how do you implement transactions? And you have to, all the problems of distributed transactions and all the cost of that, and probably also all the correctness trade-offs you have to make with that. So when you design transactions very deeply into the semantics of the system or the language, then you might run into a wall at some point with that. And it's not quite clear how you would get out of that unless you somehow extend the model.
Yeah, I mean, so what you're saying is actually related to the point that Manuel made earlier. Yeah. So the transactional semantics goes hand in hand with this view of execution as a single stream of something, okay, the single log. So there's a bottleneck there also, because if you have a single log, then you are creating a serialization there, and then you are enforcing a particular order. And now you cannot scale really, because for scalability, you just need to be able to do things in parallel. Now, if you start doing, let's say that you start doing things in parallel, you go to not single log, but maybe something like the DAG model, or you have these separate chains, or you can call them mini logs that communicate with each other, right? They are running. In that case, you can provide easily transactions on one particular, the state controlled by one particular log, but you may want something that is atomic across multiple such things. And then you're back to the problem that you were talking about, which is this distributed transaction problem. And, I mean, implementing it in a very, very general way requires taking recourse to general techniques like two-phase commit and so on. And I mean, people have tried to do that in the past. It has proven difficult because I think that you can implement two-phase commit at some cost to performance in a system where all the databases are controlled by one entity, so they can all talk the same protocol. But if the databases are controlled by different entities, then they all have to agree that they will talk this two-phase commit protocol. And I guess it has been hard.
And it might even be harder here because of trust, right? There are, like, you don't even trust all the nodes or all the chains you may be talking to.
Yes, that's right.
Yeah, so that's where you're right, Andreas, about sharding has for a long time been the kind of keyword here, the buzzword. I think recently in the last few years, there's a stronger emphasis on so-called layer 2 protocols, or I mean, there's somewhat maybe fluid progression, where sharding is basically means you take the blockchain protocol and then you split the chain into multiple chains, as you explained. Whereas layer 2 means you've got one master chain, if you like, it's the main blockchain, and then you purely via the smart contract, so the programmability of that chain without changing the protocol at all, you put maybe application specific, maybe general mechanisms on top, which actually run off-chain, but use advanced cryptography to provide scalability. And scalability is actually not just a matter of how many transactions you have to process, but it's also a data problem. I mean, if you can process very many transactions per second, you've got a hell of a lot of transactions to store, which usually also is not feasible. So actually what you want some way of saying, okay, let's say the three of us, Andreas, just myself, we want to do some things on the blockchain, exchange funds, whatever. Let us do that off the blockchain using cryptographic operations in a way that either we all three behave honestly and we work within the protocol, or either any of us tries to cheat, the other parties can go back to the main chain, prove that cheating person has been cheating, and get their funds back, or whatever the security option here is, the fallback option here is. So basically having the main blockchain as an anchor, and then having the layer 2 protocol as the thing where we interact, knowing that the security of what we are doing is backed by the main chain without the main chain having to record all those transactions. In particular, it also doesn't have to store them for perpetuity, as is the case with normal transactions. There is a lot of work on this kind of protocols at the moment, and it's tricky, but I definitely see it as a way to have this main backbone chain work in this slow but easier to understand way, because transaction by transaction things are modified, and we still can have multiple individual groups or subgroups of people do their things quickly off chain and still be backed by the security of the chain.
But then basically everybody is re-implementing the same idea ultimately, right? If like
everybody,
every group, whatever you define as a group here, would basically implement their own blockchain.
No. We want a channel protocol, which then each of these groups can use. So it's a let's say sort of application on top of the blockchain, which you as a group who wants to do something can instantiate to your current application and let it run for however long you want it, and then tear it down, settle the result on the main chain. But as a general framework, so not everybody has to re-implement their.
Is it also supposed to run forever or store a lot of data? Where would that go?
No, it doesn't have. So let me give examples. So the simplest, so motivating thing here is the Lightning network of Bitcoin. So Bitcoin is a super slow transaction rate. This whole idea of Bitcoin as electronic cash doesn't fly because Bitcoin can never get the transaction throughput. But Bitcoin Lightning is a way that it's two things. So the first thing is pairs of people can open a Lightning channel. So maybe I open one with you, Andreas, and I say, I put 3 Bitcoin into the channel, you put 3 Bitcoin into the channel. Now, if we want to pay money to each other in Bitcoin, I just send you a transaction signed, but not put on the blockchain, which says how much I sent you and vice versa. But for every transaction, we both sign them all the time. Right? We never put them onto the chain. As long as we agree what we are doing, maybe after a year we say, okay, we are done with this. We settle, okay, maybe I have 1 left and you have the other 5 Bitcoins. Now, if you suddenly run away and I'm standing there, then I can take all the signed or the summary of those signed transactions, put them onto the main chain. And even if you're running away, I can claim the funds which belong to me under the protocol we've been engaging in. Now, that's only 2 of us. So Lightning puts so-called virtual connections on top of this. So there's a routing system which routes through lots of pairs of people. So maybe you also have a connection to Chess, and I want to send some money to Chess. Then that goes via you. But you don't even need to know about that. And in this way, Lightning allows payment between lots of people, but doesn't touch the Bitcoin main chain. So it's a lot cheaper, it's very fast, and it scales. With more user, actually the network becomes better because there are more routes between every 2 people who might want to interact with each other. So this is the simplest of these type of layer 2 protocols. And there has been quite some work on also having things like contracts. Then it's called a state channel instead of a payment channel. It's a state channel, and you can run contracts in these things. But in the good case, so nobody tries to cheat, those transactions never stored on the blockchain. So you actually don't need that storage space.
But you still store them, right? So you still have something that is more or less isomorphic to having a separate chain somehow, at least in a conceptual way, because if you want to be able to, like your example, get back your coins in the case I run away, you have to be able to show all these transactions.
No. So we have a protocol, for example, it's called the Hydra Head protocol, which allows smart contracts. And the way it works, it can be more than 2 people, let's say 10 people, and they interact with each other. And then for every transaction, if I make a transaction, I create it, send it to everybody. Everybody signs it. And there's the so-called aggregate multi-signature. So that's like a cryptographic signature, but from 10 people, but it looks and has the size of a single signature, but it certifies that all 10 have signed it. And so this is how the transactions get consensus, if you like, between those 10 people. And then one round robin, we also perform snapshots. So we basically create a summary of what's the result of all the transactions we've done so far. And we also sign them, multi-sign them. So now if I have to go back to the main chain, all I have to put back is the last snapshot, which everybody still agreed on, and then the individual transactions since that last snapshot. But this is usually transaction from a very short amount of time. Everything else in the past, I don't need.
But you still like.
So the main idea is that you're storing it for a finite amount of time, and then you can GC all the old stuff.
Precisely.
Ultimately, you're still going to have the same problem that a blockchain tries to solve, right? If some of the players in the group maybe are not trustworthy, or there are some reliability, like you don't know if you can get the signature from everybody all the time. So you have to somehow have a protocol that is resilient to that, and so on and so forth. And ultimately, I think if you try to address all that, you essentially have reinvented the blockchain on the side, would be my argument.
So it is a protocol in itself, of course, but it's a generic protocol. I mean, what happens between the 10 of us can be the same things that we could do on the blockchain. So it's generic. And all the complicated cases, like what you said, people become unresponsive, somebody cheats, they're basically delegated to the blockchain, because the assumption is that's the unusual case. In the good case, people collaborate. We have to have a backup for the bad cases, for the adversarial case. In that case, as soon as I see something isn't working out the way it should, I take the last snapshots, all transactions I know about, I dump them onto the main chain in a particular contract, which is set up for this protocol. And other people maybe I want to cheat. Maybe I put an old snapshot on there. So there's a dispute protocol on the main chain, but the protocol is designed in a way that if out of the 10 people, one person is honest, that person cannot be cheated by the other 9. That's cryptographically ensured. So it's possible to have this kind of protocol. So I'm saying basically using these kind of more sophisticated cryptographic operations, we actually can have other solutions than just copying the blockchain 50 times or something like that. There's scope for things like that.
May I redirect a little bit and go back to the question we were talking about earlier about the variety of programming languages for the blockchains and virtual machine for the blockchain. And was wondering if, what are the key characteristics in your different viewpoints that make a language a blockchain language, or what are the key features and what are just accidental ones? And perhaps this could lead towards a thought of, could there be a one virtual machine that would have a common instruction set for various applications and domains?
Mm-hmm. So should I go first? All right, okay. So I remember I will say something that repeat something that Andreas said earlier, that I think that these are all, a blockchain is just another distributed system. And yes, we tried really hard to make it a really simple one. But when you try to do more with it, all the problems with distributed systems, they just come back and start to bite you. So I've come to the conclusion that the blockchain is just, another distributed system, which ends up being a little bit more open than classical distributed systems, in the sense that the participants, first of all, open in 2 different ways. So one of them is that the infrastructure on which the distributed system is running is a shared infrastructure, shared across organizations. That's one kind of sharing. The second kind of sharing is that the participants that submit commands to the system, distributed system, to be processed, they also belong to different organizations. So not only is the infrastructure shared across different organizations, the participants in the people who are sending commands into the system to be processed, they are also coming from different organizations. And I think this is, a new thing. Mm-hmm. But this is the only new thing, in my opinion. Everything else is classical distributed systems. And if you open any textbook on classical distributed systems, few things pop up. Okay, there has to be, you have to deal with global state. You have to deal with failures. So you need some kind of transactions. You need to deal with access control. So that's my view. I mean, if you build something that deals with those kinds of things, and then you kind of like pay attention, you figure out exactly where to slot the extra complexity that I was talking about, those two sources, then that might provide a general framework for thinking about this.
Manuel?
I mean, I totally agree about that it's a distributed systems problem. I also agree with your two openness points. I think there's a consequence out of this openness, and the consequence out of this openness is that in this particular sort of distributed system, cryptographic primitives become, more important is maybe the wrong way to phrase it, but they are used more widely. I mean, distributed systems have been based on some sort of cryptography for a long time. I mean, SSL, TLS, all these things are essential for the worldwide distributed systems that we have these days. And once you have participants from different organizations who don't have inherent trust between each other, then cryptography becomes the means to ensure that in a technical way. And that's why cryptography has taken over a lot of the blockchain development, because that's quite crucial. Generally speaking, to getting back to the question that we started with, different programming language, what kind of languages do we need? I mean, we have taken quite extreme stance. We have said, we don't want a new programming language. Why not? Well, making a new program, as we all know, making a new programming language is hard. Creating the tooling for a new programming language is a huge amount of work. And then you don't have a community, you don't have textbooks, you don't have university courses. So the whole thing which goes around the programming language is a huge amount of work. And I mean, I'm sure Facebook has enough resources to kind of say, okay, we'll create this. But generally speaking, I think a lot of blockchain projects, they suffer from the fact that they have this new language and there's barely any editor which does syntax highlighting for it, and the tool chain is really primitive. I mean, we are back to like 50 years ago, right, in programming environments. So our decision was to say, well, let's just use an existing programming language, and then going in the direction of what you said, just what's important here. Well, we're dealing with distributed systems, so having deterministic execution, well, that's very important. Global state is a problem. We have to control that. So going by that, thinking what kind of programming languages kind of can help us to manage this complexity to a certain extent. And so we went with purely functional programming and trying to figure out how can we have the interface to the language, the blockchain language, just as a library. In our case, a Haskell library, and then our contracts are just Haskell programs. And that has led to another, accidentally maybe, to another big advantage, namely, when we talk about smart contract language, people talk about the code which goes onto the blockchain, which is used, as just described, during validating that whether a transaction is going to go into the chain or is being thrown out again. So that's the on-chain code. But if you look at the distributed application, then there's a lot of off-chain code as well. In Ethereum, on-chain code is in Solidity, and then they have much more JavaScript around it to drive this thing, right? This is like the client versus web server. So here we have the client versus the blockchain and the on-chain code. And by using an existing programming language for the on-chain code, we can just use the same language for the off-chain code and have an integrated, a program can have both components in one module. And we are using a staged programming model to distinguish between the two.
Emmanuel, which language are you using? Are you using Haskell?
Haskell, yeah.
Okay, yeah. Nice. All right, gotcha.
So I think this speaks to the fact that trying to go with existing languages is definitely also an interesting way to go, and reuse all the infrastructure, community, and everything. And sure, you make compromises because every single language on the planet has some compromises to be. I mean, it's better at one thing than another. So you try to pick languages which fit your domain, but then you also save a lot of work.
Mm-hmm.
Yeah, I mean, I also would totally agree with what Shah said, obviously, and I would actually extend the question that Jan raised, not just to the language, but actually there's also the virtual machine, right? And each chain has its own virtual machine, and why is that? And why do they all have to be different, or what is special about them, right? And there is some emerging kind of thing that some of the blockchains at least try to be more general, including ours, and they pick just one standard virtual machine, which is like WebAssembly, for example. And then the only chain-specific thing is essentially a kind of operating system that your WebAssembly program can access, right? The chain has some operating system, but other than that, the programs you're running are regular programs. And if you use something that is a common standard like WebAssembly, you can also use any language potentially you want to run on that, right? You just need essentially access to the API, to the OS API of the chain. Maybe even some of that's in the runtime of your specific language. The programmer doesn't even have to use it manually. But I would also think that, yeah, eventually you should end up writing applications in a distributed space, just with a maybe somewhat less usual operating system underneath. Other than that, it's nothing new there.
Use in Definity.
Say again? Sorry?
What language do you use in your system?
So we have, so our VM is WebAssembly, and currently we support like two main SDKs. One is with Rust, so you can program your applications in Rust, which is fairly low level, so might not be the best choice for this kind of domain. And then we have a custom one, which is called Motoko, which we did just because there wasn't really, at the time we started like 4 years ago, a very good high-level choice for WebAssembly yet, and it's particularly not one that surfaces the distributed programming aspect nicely in the way you want it here. So Motoko is kind of like not a particularly fancy language, but it has actors as a primitive concept. So that's like your applications are essentially communicating actors. And that's all there is to it.
Okay. So to ask a question that came back, that came on the chat from Artyom. So what kind of tooling is there available for both Move and Motoko?
Okay. So I can talk about Move. So some of the tool chain I already described to you.
Yep.
In addition, there are a bunch of tools that I have not had a chance to cover. So I mean, let's see. So there is tooling around code deployment, then tooling around upgrading the modules. So once we make changes to the VM, we make changes to the Diem payment framework, and we spend considerable amount of time paying attention to the question of how to make upgrades safely. I think that this is a very, very important problem to address in this space in general. So there's some tooling, some tooling for it. In terms of just code authoring, I believe we do have syntax highlighting. There's a VS Code extension, and there is recently some work on packaging. So I think packaging, like basically, like you can think of it the equivalent of what Cargo does for Rust, the equivalent of that for Move. So there's some work going on in the team about that also. But I mean, I agree 100% with Manuel. Like building a new language ecosystem is tough. It's a lot of work, and you have to get through that grind before you actually get real data about production use. Even to get to the first meaningful data, you have to go through that grind stuff.
And I mean, some of the tooling and ecosystem infrastructure question is not just about the language itself, right? So even in our case where we say we use WebAssembly and you can just pick everything off the shelf, that's not actually true, right? Because you're running in a completely different environment than what most of the existing tool chains are built for. So even if you were to pick an off-the-shelf language, you still have to build quite a lot of tooling around it to make it workable in this environment, at least with the current state of the art, I think.
Mm-hmm.
Yeah, so I mean, so that's a fair statement, of course. We have seen a lot of benefit out of reusing Haskell. Even just teaching people how to use this stuff means, okay, we do a Haskell course or give you a Haskell book, and then after that, there's a bit on and how to use this now to program the blockchain, if you like. But it's, and that additional bit has to be there, but it's still a fraction of the overall course, basically, which we can just take from existing material. I think the most important thing is really the execution environment, because people, I mean, on one hand, like just said before, I mean, it's really important to have formal methods in this space to apply verification techniques, model checkers, and so on. But I mean, for a typical developer turnaround, we need CI integration, we need the ability to run tests and all these things. And so there needs to be, let's say, a software version of the blockchain. We call it the mock chain, which implements all the ledger rules and everything, but just as one program. So then you can write tests. So for example, I mean, being Haskellers, we use a lot of property-based testing, where we then want to be able to specify properties about if you run this contract and you apply these transitions, then at the end of the day, the chain is in a particular state, or the data on the chain, the blockchain state has particular properties. And for that, you have to be able to build up a new chain, run these traces, tear it down, look at the output for one test. Or for one run of a set of properties. So that has to happen really fast because, well, you want to run a lot of tests, right? So our focus was very much on this kind of runtime infrastructure so that you can run programs as if they run on the chain, but in a very super lightweight way, so that it just can run in the CI once you submit a pull request. And then also have feedback like, okay, this is chain state, but if it goes wrong, you need to be able to look at this chain state in a way that makes sense to the end user, or to the application programmer. So some way of visualizing the chain state and so on, so they can figure out where did my program go wrong. So I think that's where we've seen most of our work in this space has been gone.
So I'm glad, Manuel, you said that, because I missed that too. We have something like that too. So there's a way of, you use the word mock chain, right? So there's a way of basically mocking the storage captured in that is represented in a collection of move modules on disk, so that you can just run a whole bunch of functions targeting the and this is very nice. This is easy to do because there's a very clear API to what the global persistent global state is. So you can,
that's super important. That's super important. Yeah, totally agree.
If I could, if you're using existing language, be that Haskell or maybe JavaScript, do you have to cut out features of the language, or can you use it as such?
I don't think. Well, yeah, you have to cut out features. Everything that's not deterministic. So it depends a little bit on the language. If the language has a lot of indeterminism, well, you have to cut it all, because running a program twice has to give the same result. That's absolutely crucial. If you start from a language like Haskell or other purely functional languages, then that bit becomes simpler. I mean, it's not like core language features. You don't have to take a module system or types or so out, but you have to take runtime functionality out. Floating point types. Floating point types are also really bad on a blockchain because, well, floating point, anything to do with concurrency. Pardon?
We support floating points, no problem with that. There's an IEEE standard, and that's actually fully deterministic. Almost.
Okay. Yeah, I'm not saying it's impossible to have something floating point like, but if you take off the shelf floating point implementation of your random language, it can get tricky very quickly.
I see.
So this is more runtime. I mean, this is not really the language itself. It's the tie-in of the language with the runtime and the underlying architecture. And as Andreas said, it's like you run your program on a really funny operating system, and that's where you notice the difference. It's not so much the language constructs themselves.
Yeah, and that I mean, that goes back to what I said earlier, right? That affects language implementations too. So when you want to port something, like language runtimes and compilers, they usually assume all sorts of typical OS infrastructure, right? So sometimes you can't just like port it over because that functionality doesn't exist here. So what do you do about that, right? And I agree, it's actually mostly in that area where you have to do some work and where you have to cut out things and wonder how to replace them with.
So yeah, I find this question very fascinating because supposing you say use this language, okay, but I suspect that no matter which language you choose, after you tell the programmer use that language, there will be a laundry list of things you should not do. So now the thing is, the whole point of using an existing language was because it gives you familiarity. It gives you a bunch of tooling for free. Well, if at the end of the day, you are saying, don't do this, and this, is the programmer supposed to keep that in his head? Who's going to check this for the programmer? How, I mean, what is that? You have to build tooling to make sure to aid the programmer in not doing all the things that you're telling him not to do. Something has to be done, right? So this is what I find usually happens. This is kind of like the dilemma that if for a particular application with its own, or application domain with its own idiosyncrasies, if you use an existing language, you end up wanting a superset of a subset of the language. And that neither the subset nor the superset is well specified. If you try to specify it nicely and to support it with tooling, then you have to go the extra mile.
Yeah, I think so. I don't know if you have to have such a long list of things that you can't do. It's more like libraries that are not available, as Manuel said earlier, right? So for example, on the Dfinity blockchain, when you run Rust, you can use almost any Rust feature. But the inverse, the other thing you said that you also want the superset, that I actually think is the bigger problem. So for example, when you use Rust to program our blockchain, then, well, how do you write an actor? You have to use all these macros and stuff, which are like really awful and don't fit well with the Rust programming model. And you somehow have to, programmers have to deal with that, and it's not pretty. Whereas when you use Motoko, all that is kind of like part of the language, and it's a seamless experience, right? And much easier to understand and works more nicely together. But again, I think that relates to the question, like, it's a distributed system, and how many languages do we have that have good built-in support for distributed programming? Maybe that's the broader question in that regard. Because most languages still are designed as kind of like, single application kind of language. There are things like Erlang, maybe, that obviously comes to mind, but there aren't that many widely used languages that are designed with distribution in mind.
Yeah. So I will have to sort of wrap up our discussion because the next talk is coming up. So if we have last thoughts, some plug for something you want to plug or anything, then this would be the time.
There's a question, by the way. There's a new question, Jan, by the way.
Sorry. So maybe take it offline. Okay. I think it's best to type it in.
Okay, but I've got something. I've got a closing thought. I think this space is super interesting for a variety of reasons. One reason, Charles has talked about it a lot, is safety and security is super paramount here. And history on systems like Ethereum has shown the cowboy approach leads to loss of a lot of money. So it's not good enough. And I think it's an opportunity for people who are interested in programming language semantics, type system, formal verification, to really show what advanced programming language technology can do to allow normal programmers, people who are not spending the whole time thinking about program verification, to bring this technology to the point where we have tooling that a broader set of programmers can make use of, especially advanced testing and verification techniques. And I think that's a really great chance here in this space to drive this work forward. So I encourage everybody who's interested in verification, validation, and so on to maybe think about how can you apply it in this space.
Thank you, Manuel. All right. So I would like to thank our three participants, Chaz, Manuel, Andreas. It was a great discussion and a great talk. I learned a lot, and thank you very much. A big round of virtual applause to all three of you. Thanks for showing up on a Sunday, and thanks to all the audience.
Thank you very much for having us.
Yeah, thank you very much.
Thank you, guys. Thanks to everybody who attended. Bye.
Yeah, thank you.
Bye.
That starts in 10 minutes with some compiler folks. You'll see. It'll be okay. I will stop the recording now.